Sorry guys, we'll just start in few minutes. Sorry for late joining. Just give me a few seconds. We'll just start in few minutes. So we'll begin today. I'm an issue with my camera. That's why I joined lately actually. But I think it's the time and we'll start in today's sessions actually. So welcome you all to the NPTEL online certification on uh, mass transfer operations. So today we will be focusing on doing some of the concepts related to the mass transfer coefficients. But before we begin, I would like to just give a quick overview of this course on NPTEL. So this course has been offered by Professor Vishnu Mandal, and he's a professor in the Department of Chemical Engineering at IIT Guwahati. And a little bit uh, about myself is that sorry. I will be teaching assistants for this course. I am Rashmi Shubham Kumar, and I am a PMR scholar in the Department of Chemical Engineering at the Indian Institute of Technology, Madras. So I will be the course TA for this entire tenure of this course, that is from uh, this session, that is from July to November. So every weekend we will having this online live interaction on Saturday, that is from 3 to 4 p.m. So for today we will be having like for the week 3 is over. So for the week 1 and week 2, we just went through the uh, like the basics of mass transfer operations, and along with that what we did is that just yeah, now it's fine. So what we did, okay, it's lagging, but let's see if it's working. So for the week 3, uh, just 1 minute second. Okay, so we'll begin. So for the week 3, there is a concepts related to the mass transfer coefficients, and like the mass transfer coefficients related to the concepts of gas, liquid, and solids, and the prediction and the diffusivity behavior like turbulent and a laminar flow. So we'll start. So the content for the week 3 as mentioned on the NPTEL swim portal is like somewhat this. I'm just mentioning just to make sure like you guys have already gone through the week 3 lecture notes before we prior solving some of the numerical questions for today. So that it's involved mass transfer coefficients, concepts and classifications, dimensionless groups, which specifically talks about the mass transfer coefficients in lambda flow, like I said just now, and the boundary layer concept theory, which is the form of the turbulent flow concepts in the mass transfer coefficients. Okay, so these are the various concepts that has been told in the week three concepts. So it basically talks about the MTC, that is the mass transfer coefficients concepts. So these are some of the basic like the concepts that week 3 has been covered, and Before starting, we will go like just a quick overview why mass transfer coefficients and why they have been studied. Okay, so the first one is uh, what is mass transfer coefficient. The second one, like the different types of mass transfer coefficients. And similarly, like studied in for diffusivity of A with respect to non-diffusing B and equimolar counter diffusion, similarly mass transfer coefficients are there in terms of this. So there will be of diffusion of through non-diffusing B, and similarly equimolar counter diffusion will also be there in case of mass transfer coefficients. Equimolar counter diffusion. So these are the same, this is 3 and 4 are the same concepts we have already been studied. And the last one is the relating between the different mass transfer coefficients. So there will be relation between the mass transfer coefficients, because there are different types like Kg, Ky, Kc, Kp. So these are the various on the basis of liquid and gas and solids. Okay, so uh, apart from this, if you, I will choose different color. So if you take the rate of mass transfer, it is directly proportional to the concentration driving force. Okay, so this is the thing that we already gone through the lecture note, but I'm still writing in order to get a quick overview. Driving force, there is a difference in the concentration gradient. So for the rate of mass transfer is also been directly proportional to the area of the contact between the phases. So it can also be directly proportional to the area of contact between the phases. Okay, so these are just the basic rule out which I've already gone through the lecture notes. So if you take W as a rate of mass transfer, rate of, I'm writing in shortcut as the rate of mass transfer, that is in mole per second, or you can write as kilomole per second of species A. If you consider as a solid or solid, if you consider solute A, and delta C is a concentration difference or the concentration driving force. So the driving force between the 2 points, or you can consider anything, and we can take A is the area of mass transfer. Therefore, we can write the rate of mass transfer of the species soluted A is directly proportional to the concentration gradient, that is delta Ca into the area A. Therefore, rate of mass transfer of the solid species is equal to, we can place a constant here, that is Ka A delta Ca. So this equation you can write, and this is none other than the mass transfer coefficient, that is known as the mass transfer coefficient for proportionality constant, or you can say the mass transfer coefficient. So we have different types of mass transfer coefficient we have already gone through, and we can write the unit for this, the mass transfer coefficient. So if you take Na as a mole of flux, like Na Like we already gone through the molar flux and Na and Ga, like the fixed location space, and one is related to the average molar velocities of the species involved. So Na is the, if you take Na as a molar flux, expressed is in similarly kilomole per meter square into second. Therefore, Wa is equal to A into Na is equal to Kca delta Ca. Similarly, we have just replaced from the previous equation. Therefore, mass transfer coefficient we can write Kc equal to Na upon delta Ca from the above equation, this one. Okay. So this comes out to be good. So the N is the molar flux divided by the driving force or concentration driving force or concentration gradient. Okay. So similarly, we have the heat transfer coefficient and various other concepts. So now there is another term called the mass transfer coefficient. There is another term called mass transfer resistance. Right in different. So that is mass transfer resistance. And this term has been the reciprocal of the term that we have already derived about, that is the mass transfer. So the so it is, I'm just writing in the short note, it is the reciprocal of mass transfer coefficient, and units will be the inverse of this, that is what you can write, the unit is inverse of, I'll just delete this one so it's not making any difference. So if you write in mass transfer resistance, this inversion is probably 1 upon mass transfer coefficient. So this is another one, like 1 mark question if they asked in the final examinations. Okay. So similarly, there are like different types of mass transfer coefficient, like I say, like Kg, Ky, Kc, Kp. So the Kc is related to the mass transfer coefficient in the liquids, Kp is related to the partial pressure of the gases, and Ky is related to the fraction concentration related to the vapor or gases in the system involved. And similarly, like at the different pressures, and there will be some different concepts. So this all depends upon the driving forces. So the driving force will be based depend upon the concentration gradient, like we started from the mass transfer courses. It is based related to the mass concentration gradient or the driving force in the pressure, partial pressure or in the mole fraction difference. So these are some of the driving forces. Okay, so now we have seen like some of the different things, like many things that have been involved here. That is the flux, driving force, and the various driving forces for the mass transfer. That is concentration gradient, partial pressure, and the difference in the mole fraction. And so, in in general, we can write flux x mass transfer coefficient into the driving force. So this can be easily be derived, and so after looking at all the above basic concepts, you can go for the various things. And also, I will just quickly write a one a relation between Kj, Ky, and Kc. So this uh, mass transfer coefficient in gas phase. So it's been rated as Na equal to, sorry guys. So this is the relation in, no problem, I'll just write it again. So mass transfer coefficient in gas phase. Okay, so it's given as relation as N equal to Kg. Kg is the mass transfer coefficient of gas phase related to the partial pressure P1 minus Pa2 is kg, ky y1 minus ya2 equal to kc ca1 minus ca2, that is the concentration gradient in the vapor phase with partial pressure and this. So these are the gas phase mass transfer coefficient, that is kg, ky and kc. Similarly in the liquids, I'll just write up here liquid phase mass transfer coefficients. So it can be related as Na is equal to Kx, that is the liquid phase mole fraction, Xa1 minus Xa2 is equal to Kl Ca1 minus Ca2. So similarly, there are so many relations like kg dash ky dash. So if you've gone through the lecture notes, because the only thing that changes is the different terms. Instead of Ca, you can write Xa, because Ca is going to Pa by RT. I can relate with the terms of partial pressure, and so many things can be done with that. So this is that I mentioned in order to get a hand-on experience for the basics of the mass transfer coefficients and how gas phase and liquid phase and solid phase mass transfer coefficients have been derived, and the basic definition of what is mass transfer coefficient like we have done here. And apart from that, we have seen the mass transfer coefficients in gases and liquid. So right now we will start with one of the basic question, and these are some of the like concepts like the different dimensionality terms known in the mass transfer. So So this is one of the question, like it's been there in the assignments also, but I think it's much more related to the concept that we already gone. So this question talks about the general equation for steady state diffusion through the variable area or the variable cross section area can be related as. So just go through the question first of all and see all the like the options that has been given up here. So first of all, what we need to see is that the general equation they have been asking for the steady state molecular diffusion to the variable cross section area. So this we have already done the last week, that is a cross section area, various cross section area, that is a flow through a convex, flow through a sphere. I have also derived one equation and I mentioned in the lecture notes also, but here we will see how it's been related. Okay, so now I've already said what is flux. That is I've already mentioned flux as mass transfer coefficient into the driving force that I've mentioned up here. Okay, and they have asked what the general equation for the steady state diffusion through a variable cross section area. So what do you guys think the correct answer for this will be? If its area is related to the flux and how it will be constant, because flux is equal to the mass transfer coefficient into the driving force. So driving force can be anything if there is a concentration difference or partial pressure difference or the mole fraction difference. So what they have given is for the variable cross section area, flux into area will be constant or flux into volume will be constant, and the similar for the type. So this, if you have seen the previous notes, what I have just written here right now, you can see there is a relation between flux and the area, and uh, flux is inversely proportional to the area, and if you take both the terms and multiply with each other, then you will get a constant value. So the correct answer for the variable cross section area is that flux into area is constant. So this is one of the basic concept that we just studied right now, and we know how to just quickly go through the concepts. And before this also, there are many parameters like or two. Apart from this question, in examinations also they will ask what will the gas phase and the liquid phase mass transfer coefficients typical values. So I'll just write down. So this is not related to this question. Consider question one. This is just note I am writing down, because in many examinations like GATE and NPTEL or online examinations also they will ask you regarding the direct values for this. So the gas phase mass transfer coefficient value. So these are the typical values we can write at Kc is directly proportional 10⁻², meter square per second, and similarly second is liquid phase mass transfer coefficient values That is, you can give as Kc is the order of 10 is to minus 5. So these two values, that is 10 is to minus 2 and 10 is to minus 5, this can be directly be asked in the final examinations. So this also has a derivations, these two values, but it's better to remember if it's like quick 1 mark question for the final exam. But I will suggest just keep in mind about these values. So these are generally for the film thickness of variable like zero point 0.1 to 1 mm. So the gas phase value what I mentioned is for the film thickness of you can say approximately 1 mm, and this is for the film thickness of approximately zero point 0.1 mm. So these are some of the parameters, but they will generally ask what is the value of the mass transfer coefficient Kc. Okay, so this is one of the things that you need to remember. We'll move to the next question. This is the question 2, and it says choose a quantity that has an influence on the mass transfer coefficient. So we just now read what is mass transfer coefficient and why we have derived mass transfer coefficients for the laminar and the turbulent flow, and why we change this more like flux, that is Na, with respect to like some of the terms Wa, because which is directly proportional to the concentration variance and the area for that term. But why, which quantity has more influence on the mass transfer coefficient? If it's diffusivity, hydrodynamics of the system, viscosity of the system, or all of the above. So basically, if you see all the concepts that has been relating mass transfer coefficient, there is an area, concentration difference, and so many things are coming up. And this mass transfer coefficient are basically been derived for the turbulent flow systems because of the viscosity and the eddies that is forming at a turbulent flow system, and also for the laminar one. So mass transfer coefficient has been affected by diffusivity, that is the correct one. It also been affected by the hydrodynamics, that is the turbulence and the eddies formation. And the third one is the viscosity, means how much the Reynolds number will be there, because Reynolds number will indirectly affect the flow of the system, that however it will be turbulent or laminar flow. So if you see of all the options, all three options are correct. So the correct one will be D, that is all of the above, because mass transfer coefficient is related to all the things indirectly, not directly you can say, but indirectly they have been related. So all these things will indirectly, directly or indirectly affect the mass transfer coefficients. So now this we comes up to some relation related to the dimensionless coefficients or the dimensionless numbers, which are terminologies in heat like mass transfer, like momentum and mass transfer. Similarly, there are terminologies in heat transfer, heat mass and momentum transfer terminologies are there. So in mass transfer, we'll go through some of the terminologies which relates the dimensionless numbers. As you can see here, there are 4 different dimensionless numbers that have been mentioned. Before going to the question, we'll see what is Sherwood number, Reynolds number, and Schmidt number. So if you can see, Reynolds number is a well known. It defines whether the flow is laminar or turbulent flow. So before, if you can consider 2000, or if I take the approximate under, it's laminar, and above 4000, it's turbulent. Okay, and in between these two regions, that is 2100 to 4000, this corresponds to the transition or transition behavior. Okay, so these two and these are the 3 different values of the Reynolds number, but you can write Reynolds number as rho v d pi mu, where rho is the density, v is the velocity, d is the diameter of the system which it is flowing, and mu is the viscosity. So similarly, it can be write in terms of the kinematic viscosity, that is rho dy kinetic viscosity k. And similarly, what has been given here is that because Reynolds number is a dimensionless number, similarly there are many dimensionless numbers which have the terminologies related to the mass and momentum transfer analogies. So what has been written here is what is the Stanton number for mass transfer. Similarly, analogy is there for the heat transfer. So if you know how to relate Stanton number with the Sherwood and the Schmidt number, because Schmidt number, if you can write, it's like I think by rho d or rho by mu d. So I'm not relating that all, because all these different terms have a different relation with each other. But if you have seen the derivations, or if you know what is the concept of Stanton number and how it is related, you can see that it's related to the Sherwood number divided by Reynolds into Schmidt number. So the all the symbols have their actual usual meaning, and all they have like inertia force to the viscous force, that is force for the Reynolds number is all about. So similarly, if you see the Stanton number is related to the Sherwood number by Reynolds into Sheetman number. This is just because you need to involve all these formulas, and the formula for the Stanton number will arrive. So I'm not solving each and everything right here, but it's just basically just I'm showing that there are many dimensional terms. You have already gone through the lecture notes. I also wanted to show like some of the derivations, but since we are time bounded, we are just seeing how the Stanton number is being related to the Reynolds and Sheetmate. So similarly, Sheetmate number will be there, and Prandtl number will also be there. So these three, like these 4 to 5 different terms, like basically I will say, if you want to derive each and every dimensionless numbers, we first have to go through the Reynolds number, Prandtl number, and Sheetman number. You just know these three numbers and the derivations and the definitions. What will come, like inertia to the viscous, momentum to the molecular diffusivity, and that all. Apart from that, you can derive anything, that is Stanton number, Packlet number, anything. So just you know what is this three number about and how they have been related with each other. The other things come because of the Blair relation, that is the analogous in mass and momentum transfer. Okay, so this one is question 4. I'm just going quickly through this question because there's a 1 marks MCQ. So, given that physical significance of Sheet number is a ratio of, so like I said, shipment number is mu by rho d. I have not mentioned the previous thing, but I'm saying it's like viscosity by density into diffusivity or the diameter. So what is the physical significance? Like the physical significance for the Reynolds number will be rho v d by mu. That is the initial force to the viscous force. That is the first question about. So it nullifies here. Whereas for the Shidman number, like I have mentioned here, what is the Shidman mu by rho d? Okay, so if you see this, there is like diffusivity constant term here. So it generally relates to the momentum diffusivity to the molecular diffusivity. So, so if you know the formula or the definitions, how is it related, similar to the Reynolds number, Sheetmate number, Prandtl number, and Sherwood or Stanton number, Packlet number will be the same. So all these have been relation with each other, and it's just like a quickly derivation from one to another to third one. So what I will suggest is just go like some, remember only three, what you can say, like Reynolds number, parental, and Sheetmate number. Apart from that, all the other dimensionless numbers you can derive easily, and you don't even have to remember this definitions, whether it's like momentum or molecular or anything, because once you know these three different dimensionless numbers in mass transfer, the other all the things can be derived easily because they are all been interrelated to each other. Okay, so this is how we are going to use these concepts and how we are going to apply it to the various the questions for solving the answer, because all these different terms will directly come into the questions, and how, and it depends upon how you use these formulas, like directly what is Shidbin number, into the questions for arriving at a particular answer. So before going to solving like some questions related to what is involving Shidbin number or anything, you guys must know what is actually that thing. Okay, so this is just mentioning what is Sydney, parental, Sherwood, and how they are interrelated. That is the analogous behavior. So this is another term, like I said. So we show what is Sherwood number, Shidman number, Reynolds number, and what is Shipman number, physical significance means. Similarly, there is a Lewis number which is related to the like two different terms. So apart from these four different options, what do you think will be the correct answer? Because there is Lewis number term for gases also and liquids also there are there, but it has a typical value. I'm not giving that typical value here because as we proceed through the courses, I will just quickly go through all the values like they have been asked in the final exams as well as in the gate examinations. But it's better to learn what is actually the basic meaning is and how they are physically significant related to the particular term. So, can anyone say what is Lewis number? It's just the relation between two different dimensionless number. So, out of the four options given here, what will be the correct answer? Just a quick guess, what will be the Lewis number? Either it will be Sherwood number to Nusselt, So I'll just quickly give you a hint that Lewis number is related to the Schmidt and the Prandtl number. So what will be the correct answer? So Lewis number has been represented by Le. Anyone just a quick guess what is Lewis number? Because it's already been covered in the lecture notes. I'm just revising you guys so that it's better to get revised what has been covered in the lectures. So it's better for you to solve the assignment problems also quickly. So if you have not gone through the lecture notes, I'll suggest you guys please go through the lecture notes once more and let me know if you have any problems in the lecture notes, because I'm also trying to cover up some of the quick concepts prior to solving some of the questions, because if I directly go to the questions, there's no, that doesn't make any meaning to arrive at a particular answer, because if someone does knows what is the basic concept that has been covered during the entire week session, it's not a better idea to go directly solve the questions. That's why I'm covering the concepts in a quick go, like 15 to 20 minutes what has been covered through the week, and then on the basic of that what assignments problems have been given to you guys, and the similar questions that we can solve using the same concepts during the entire week tenure of the course. So so the Lewis number is related to the Schmidt and a parental number, but how it's been related? Either it is Schmidt to the parental or parental to the Schmidt number. I think this is a quick one, and you can guess is easily. It's not that much difficult, because Lewis number has its own significance, which I have not mentioned up here. But I think if someone is like having difficulty, I will suggest this guy to go through the notes and let's see. So the Lewis number is equal to the Schmidt to the parental number. Or I'm just asking whether is this parentable or Schmidt. So just let's see, we'll see in a later point of time what is actually, because if no one is answering, then it's better to quickly. So what I will do, I will take this concept like for the Lewis number and Lewis number how is related to the other thing in the next class, because I have not shown you the physical significance of the Lewis number in this class. So what I will do, I will cover up all the concepts related to the Lewis, as well as what I will do, I will relate all the concepts for Reynolds number, parental number, Schmidt number, Sherwood number, Stanton number, and all the dimensionless numbers and their analogies in mass transfer in next lecture. Because I think relating this analogies is like one of the things that you guys must remember, because it carries a huge, like, 2 to 3 marks in the final examination. That's why I'm just showing like questions, but in the next lecture what I will do, we will start just quickly with this 5 to 10 minutes on this dimensionless numbers and how to relate these analogies with each other. Okay, meanwhile we'll just move on the second this question. So this question I have directly taken from the lecture notes, and if you've gone through the lecture notes, this is one of the questions that has already been taught in the week 3 beginning. So what it says is that large volume of pure N2 gas at atmospheric pressure is flowing over a pool of liquid of methanol, which is evaporating. So the N2 is assumed to be the insolvent liquid. So it's like the diffusion of A to non-diffusing B, and A is diffusing through non-diffusing B. So the gas phase mass transfer coefficient of methanol is Kg. So the Kg has been given to us is 2.5 to 10 is to minus 5 kilomole per meter square second, kilopascal. Assuming the vapor pressure of methanol is given at a temperature of, that is a room temperature, is 10 kilopascal, calculate kg. Kg has been given. They need us to calculate ky, kc, ky, and the flux. And similarly, what is the diffusivity of methanol at this temperature is given. This, calculate the thickness of the gas frame. So these are the 3 different terms. We will start with the first one quickly. So the total pressure is on atmosphere, that is 101.3 kilopascal. Written in terms of kilopascal, if you write in terms of particle pascal, it will be 101.325 pascal. And if you want to write in the same in the terms of bar, it will be 1.01325 into 10 to 5 bar. Okay, and R, that is a universal gas constant, we can take it as, there are different values for the R also, so this depends on the type of the units given in the questions, because we need to take all the units in the same values. So for considering this, I am taking 0.082 meter cube atmosphere per kilomole into Kelvin. So I will convert this atmosphere into the Pascal or kilopascal, so that I can write as 0.082 into 101.3 meter cube kilopascal per kilomole into Kelvin. Okay, so this can turns out to be 8.3066 meter cube into Pascal kilomole into Kelvin. And the temperature has been given to us at room temperature, that is 273.15 Kelvin plus 25 degrees Celsius. If I can take, that is given as 298 Kelvin. Okay, so we know that the relation between kg, ky, kc. So they have asked us to, they have given kg, they want to calculate as ky. So the ky will be kg into. So this is a relation you can derive from the previous one. So the kg is given as 2 into 10 is to minus 5 into pt, that is total pressure is 101.3. This comes out to be, if you solve it, 2, that is 2.03 into 10 is to minus 3. The unit will be kilomole just per second. Okay. So this is what kg is related, and similarly you can derive kc. Kc is equal to kg into rt. Kg is already given as 2 into 10 is to minus 5. R is we derived as meter cube kilopascal into kilomole Kelvin, that is 8.3066 into temperature, that is 298 Kelvin. So this comes out to be 0.0495 meter per second. Now, in order to derive ky, so ky has another, so we have derived these two terms, ky, uh, kc, and we also know that ky can be related to the partial pressure terms with respect to kg, that is kg 1 by. Okay, now given to us is PA1, that is 10 kilopascal in the question already. I will show you where is that. Given to us the assumed vapor pressure of the methanol. If we take A as methanol and B as N2, so it's given as 10 kilopascal. So take as PA1 is equal to 10 kilopascal. Therefore PT we already know. So PA1 plus PB1 equal to PT. So PB1 will be PT minus P1 is equal to 101.3 minus 10 kilopascal. It comes out to be 91.3 kPa. Also, since partial pressure of 2 is 0, so we can take PB2 equal to PT equal to 101.3 kPa. So these two have already been derived, and what we'll do, we just calculate the value here. Therefore, Ky equal to Kg, that is 2 into 10 to the minus 5 into bracket PB1 is derived as 91.3 into PB2 is 101.3 divided PT, that is the total pressure is 101.3 kilopascal. So this comes out to be 1.83 into 10 to the minus 3 kilomole per meter square into second. Okay, now the flux they have been mentioned because they need us to calculate kg, ky, kc. We have calculated, and you want to calculate the f. So what we derived right now is the capital Ky. So this terms, just rewrite it. So this is capital Ky. that is small k1. Okay, so this we have read kg, ky, small k1, capital K1. Now we need to derive the flux, that is the F. So F will be kg into PBLM, that is a logarithmic pressure difference. So kg is 2 into 10 is to minus 5 into PBLM will be PB2 minus PB1 divided by ln of PB2 by PB1. So this is comes out to be, I'm writing this here, 2 into 10 is to minus 5 into PB2 is 101.3 minus 91.3 divided by ln of 101.3 divided by 91.3. So this comes out to be, if you solve it using the scientific calculator, it's much more easier to do in scientific calculator in one go, into 10 is to minus 3 kilomole per meter square into second. So this is what F, that is the flux. Now the main question arises at the second one. So this is F. So what they have asked in the second question, this is one we are done. So the second one is calculate the diffusivity of methanol at 298 Kelvin. Okay, so diffusivity of methanol they have given to us at the room temperature, that is 2 into 10 to minus 5 meters per second. Calculate the thickness of the gas film. Okay, so now we need to calculate the thickness. So how to do that? First of all, so this is somewhat related to the boundary concepts and somewhat, but already I'm not going to say what is boundary layer theory, each and everything. I'll just try to solve it out how it's been related. So the diffusivity is, you can write DAB, it's 2 into 10 is to minus 5 meters square per second, and the total pressure is given to us at 101.3 kilopascal. And R we can take it as 0.082 that is in meter cube atmosphere per kilomole into Kelvin, or you can write it as 8.3066 8.3066 sorry, meters cube into kilopascal per kilomole into Kelvin. Okay, and temperature is given to us at 298 Kelvin. And kg we have already derived, that's value come out to be, or it's already been given. Okay, so we have kg also. So now to derive this formula for the thickness, there is a particular value in which you can relate. So if you can see, kg is related to the diffusivity to the total pressure divided by RT into PBLM. Okay, so if you place this interrelate with all these things, that means if I want to rearrange all these things, you can write the thickness of the film as dV pt upon RT into kg into PBLM. So this is one of the relation. I'm not going to derive it here, but the only thing is that we can directly put all these values here so you can get the answer quickly. So we have already derived what is PBLM, that is here. Logarithmic mean pressure difference for the partial pressure B. So if you put all the values in this equation, we have DAB, we have total pressure, we know R, T, Kg and PBLM. We'll get the thickness value as 0.425 mm. So how these two concepts has been related, and how the film thickness can vary according to the flow. So all these things you can derive easily. The only thing is that if you know the basics of the mass transfer coefficients, which we have covered during this course, and some of the terminologies like I like to cover again in the next course, because it's somewhat like similar terminologies in the heat transfer, and the same terminologies will be there in the mass transfer also. So it's better that I will cover in the next weekend, like in next Saturday at 3 to 4. First of all, I will cover what are the basic uh, this dimensionless quantities and the mass transfer analogies and the relation with each other, because it covers like almost 2 to 3 marks or more than that in the final examinations also, because it's just a quick go. If you remember like some dimensionless numbers, you can easily solve the questions very easily. So in the next class, we'll go through first of all these concepts, and we'll try to wind it up regarding this mass transfer coefficients, and we'll proceed further. So this is what I have for today, that is for the mass transfer coefficients, some of the dimensionless numbers, and some questions related to how to solve this mass transfer coefficients related terms in the terms of like what we solved in the last question. So I think in most of these assignments problems related to assignment 3, that is the big 3 assignment, it has been related to this mass transfer coefficients. So I suggest you guys, its deadline has not been ended till now, it's just like more than 1 or 2 week time. So I suggested to go through the lecture notes once again, because it's better, because from now onwards the course will pick up, and I don't want any one of you to lag behind, because it's better to revise every time and just solve it out every questions that you have in the this live interactions and anything. So this is what I have for today. If any one of you have any questions, just let me know right now. Otherwise, we will meet next week. Do anyone have any questions related to the concepts that we discussed today? I know some of the concepts we will discuss in the next week related to the mass transfer coefficients, particularly related to the dimensionless quantities and their analogous behavior. So if no one have any question today, we will meet up next week at the same time, that is a Saturday 3 to 4. Just try to, so I will start with this mass transfer analogies first, then I will proceed with week 4 courses, week 4's concepts in the next uh, weekend, that is on next Saturday 3 to 4. So thank you. If no one has any question, we will meet up next week at the same time 3 to 4 for solving some of the concepts related to mass transfer coefficient, dimensionless numbers, and the week 4 concepts. Till then, uh, take care, goodbye. And any one of you have any issues, and if you are facing some issues, not if someone of you are not asking anything in this live interaction, it's better to ask by through mail or through put some questions in the forum, so I will able to answer there also. It's not anything yet. If you are facing difficulties during the week time also, just drop a mail to the NPTEL and the NPTEL Swayam portal. You can create a forum. There's a forum also, you can ask any questions related to that for assignments. So it's better to go through the lecture notes again and again, and let's see what you can bring out from that. Okay, till then, goodbye. We'll see you next week. This is what I have for today. Thank you all, guys. Thank you for joining. We'll meet up next week, that is on Saturday 3 to 4. Thank you.